Hello everyone! In this video, planet Earth, the Sun and other stars will face off against a massive black hole, all using the simulator Universe Sandbox. Let's get started! And the first experiment will be to see what happens if Earth flies directly toward the black hole. This is what it all looks like, very close to the black hole. By the way, the black hole has a mass of 1 million suns. And look what's already starting to happen to Earth. Look at that, it's heating up incredibly. The maximum temperature is already 135,000 degrees Celsius, and the average is around 5,000 degrees. Before it flies into the black hole, I want to go down to our planet and see what this black hole looks like in the sky. And here we are. I'm looking at the black hole from the surface of Earth, and we can see this mesmerizing spectacle in the sky. Wow, this is incredible. So there you have it. I'm on Earth and this is what it all looks like. In the simulator, time is currently passing at 1 second per second, and so this is the spaghetti effect we get if we guide Earth in front of the black hole. Well, that's pretty cool, of course. Planet Earth, as we can see, is passing through the accretion disk of this black hole. And now it's going to approach the event horizon. Let's see what happens to Earth next. But a lot of fragments are flying off of Earth. The Roche limit, all that stuff. Earth is just being destroyed. Its temperature is actually dropping, as we can see, but at the same time the minimum temperature is rising. So the temperature is just averaging out across the planet. And its mass has already decreased a little bit, which makes sense. Our planet is somewhere around here, and as you can see, it's about to be swallowed up. Before that happens, let's see how it all plays out. Earth just disappeared, guys. Earth dissolved in the black hole, or was simply swallowed by the black hole. Well, there you have it. In the next experiment, I'll take our star, the Sun, and launch it into a direct collision with the black hole. I'll set the time in the simulator to 10 seconds per second. The Sun is beginning its approach to the black hole. Let's see how this collision plays out in the case of a star. This is also what you get if you guide a star in front of a black hole. You get this kind of spaghetti effect. Not bad. I decided to check the Sun's speed here, and it's almost 20% of the speed of light. That's really fast. As we remember, Earth was torn apart in the last experiment. In principle, the same thing should happen to the Sun. Well, we'll find out now if the outcome will be the same. There's just a little bit left until the accretion disk. We're about to enter it. We're entering the accretion disk. The Sun immediately changed its color. I'll slow down time. Let's see how it all happens. And so the star approaches, heading straight for the event horizon. And what? Will it just disappear like that? Or will something more interesting happen? Oh my. Look how it's being stretched out, as if the black hole disappeared from view, and the star also just vanished. That was a bit boring, but oh well. With direct collisions, it's clear. Now let's try to put the Sun into a close orbit around the black hole. I'll place the Sun at a distance of about 0.1 astronomical units from the black hole, and I'll start the simulation. The motion has begun and the Sun is starting to be torn apart. Just completely and utterly torn apart. If we look at it like this, we can see the black hole is forming an accretion disk. But you have to agree, this looks much more interesting. Well, that makes sense. Let's add another Sun. I decided to add another Sun and saturate this accretion disk. I'll place it at the same distance as last time, 0.1 astronomical units from the black hole. I've started the simulation. Let's see how this Sun will also be torn to pieces, forming a denser accretion disk around the black hole. The Sun isn't being torn apart yet, but we need to speed up time and then it should happen. Yes, as we can see it's being torn apart. Let's look at it like this again. And now the accretion disk looks even better and more saturated. Well, that's cool. Now we can in principle switch back to the normal background display like we had before, because the black hole is already illuminating everything around it, thanks to the accretion disk. And now I'll try to place Earth here, close to the black hole, and we'll see if the temperature will be comfortable for Earth, if all of this will heat our planet Earth. I'll place Earth at a distance of about 0.2 astronomical units from the black hole. This is how Earth is illuminated by the black hole. Everything is very bright. The temperature isn't changing yet. We need to speed up time more. I'll speed it up to 100 seconds per second. Even more. Whoa, 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 whoa. Did you just see that? Oh, more. Earth is just being torn to pieces. There it goes again and again, just like that. I'll slow down time a bit to get a closer look, and Earth is just crumbling, guys. At this distance, Earth can't exist normally. Well, you can see for yourselves, the Roche limit is just very close to the black hole. Earth needs to be placed further away for it to be okay. Oh, it looks like the accretion disk around the black hole is starting to suffer. Oh well. Anyway, I decided to redo everything. I'll form the accretion disk again using 2 suns. Here, watch again how it all happens. You could watch this for a long time because it looks so beautiful and mesmerizing. Well, the accretion disk is forming beautifully. It's wonderful. Now I'll take Earth and place it in a distant orbit around the black hole, let's say at a distance of 2 astronomical units. Okay, everything is ready. There's the black hole, and this is what it looks like from this distance. And so I've started this simulation. 1 month is passing per second, and we can see the temperature has already risen to 30 degrees Celsius, and it just keeps rising and rising. Even at a distance of 2 astronomical units, the influence of that black hole is enormous. Well, the black hole is extremely massive, with a mass of 1 million solar masses. It's incredible. And yes, the temperature is very high, life on Earth is starting to disappear. In Europe, the vegetation has disappeared. In North America too. So, it's all clear. It's going to be very hot here. And now I want to show you what the approach to the black hole and being swallowed by it will look like from the surface of Earth. While all of this is happening, I'll land somewhere in North America. And let's turn our attention upward to the vast sky and watch together as the black hole approaches. So this is what it all looks like. Let's watch. And we're about to go in there, guys. This is just epic. This is epic. Let's slow down time before we get closer. Whoa, 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 whoa. You can't make anything out. Everything is already so intense here. It's lagging a bit, but that's okay. Oh, it's all blinding. You can't see anything at all. It's lagging. Lagging the whole time. I guess we're just going to fall into eternal darkness now. Yeah, you can't see anything. It's just, nothing's clear. You can't see anything. So, well, that's it. So that's it. But you have to admit, it was cool to watch it like that. Next, we'll take bigger and significantly more massive stars and see how the black hole actually deals with them in this process. Let's start with the star Procyon. This star is bigger than the Sun, and this time I'll place it a bit further away at a distance of 0.2 astronomical units. Russian is on its way. I'm speeding up time. It's not being torn apart yet, but I think it's just a matter of time. Oh, there it is. It's starting to tear apart. And now it looks like another layer of the accretion disk will be created. Okay, speeding up. This is how it all happens, so watch and enjoy. And that's it, the star was torn apart very quickly, and it created something like an outer ring of the accretion disk. If you look at it like this is what it all looks like. There's still a small piece of the star left here. I guess it's the core that's left. Well, the mass isn't large, 57 Jupiter masses, and the radius is like 4 Earths. Now I'll take a bigger star. This time I think Pollux will be perfect. And let's put it at a distance of 0.3 astronomical units from the center of the black hole. Pollux is also being torn apart. The black hole is pulling out matter, substance, and feeding its accretion disk. It's all being torn apart so quickly it seems a bit unnatural. I decided to completely restart the simulator so it would work properly, because sometimes these bugs in Universe Sandbox get annoying. And I've also placed Pollux at a distance of 0.3 astronomical units, launching the simulation. Whoa, everything's so fast. Why didn't I slow down time? Oh no. So, this is my third attempt. I've already slowed down time, and I'm placing the star Pollux at a distance of 0.3 astronomical units from the center of the black hole. I'm starting the simulation. This time, 5 minutes are passing per second. And there we go, the animation is now starting. The black hole is pulling out matter from the star. This time I really hope it won't happen so quickly. Honestly, the star should last much longer after all. No, look, it disintegrated almost instantly. Well, I guess that's just how it's processed in this simulation. Okay, if that's the case, I'll try just placing the most massive star around this black hole. Let's take R13601 with a mass of 260 solar masses, according to Universe Sandbox. I'll place this star at the same distance as Pollux. The movement has started. For now, the star is feeling normal, but that's for now. Let's speed up time a bit. It should be torn apart too, I think. Still, the black hole is more massive than this star, even though this star is the most massive one in the universe discovered at the time of filming this video. Look, it's holding up well for now. It's lasting a long time, not tearing apart. Oh, something's happening. Some fragments just flew off. Still, little by little, R13601 is starting to lose its mass. The black hole is siphoning it off. Oh, more matter just broke free. And now matter is really starting to be torn away. Let me show you. Well, right now it's even showing the mass of R13601 is increasing. It increases, then decreases, but overall it's increasing more than it's decreasing. I guess it absorbed the neighboring gases, the ones from Pollux maybe. It's such a massive star that it's not giving up to this supermassive black hole so easily. I'll speed up time to 15 minutes per second. Let's watch the mass. It looks like it's starting to lose ground now, and the black hole is beginning to get the upper hand over this star. And look how many fragments have been ejected here. It's incredible. Though all of this isn't creating a proper accretion disk because, well, everything is scattered and uneven. I'll speed up time even more. Let's make it happen faster and see the outcome. Well, R13601 has a lot of matter, so the black hole needs time to absorb it all, tear it apart, and so on. The mass is already down to 150 solar masses. R13601, as you saw, was getting incredibly close to the black hole little by little, but it went right inside the black hole. And everything changed. The color of the accretion disk changed immediately. Alright, I'll remove all these fragments. And now, let's see how this black hole will handle the largest star currently known and discovered at the time of filming this video, the star Stephenson 218 in the universe. I'll place this star at a distance of 12 astronomical units from the black hole. Compared to the black hole, the star is just enormous, as you can see. Starting the simulation. And we can see the black hole starting to siphon matter from Stephenson. It's perfectly clear from this angle. Well, even if we look from here, you can clearly see matter being torn away, right where the black hole is, right here. If we take a closer look, you can clearly see that Stephenson's mass is actively decreasing. And now, let's see how this all ends. The star just turned blue. I guess it heated up and it started to grow and it got absorbed. I think it started absorbing the gases that were being ejected maybe, although those were its own gases, but for some reason it grew and eventually reached the black hole. Well, that's how the Universe Sandbox simulator processed it. And after that we see these beautiful hot gases flying around the black hole. And so that's the result of this experiment. Please give it a like and write what you think about what you saw in the comments below. We really appreciate your support. Thank you very much for watching, and until the next experiments in the universe.